So the next part of this lecture is the IoT architecture of four layers reference model. Engineers use what is called the four-layer reference model to describe the different responsibilities within an IoT system. Think of it like the floor of a building. Each floor has a distinct role, but the building only works when all floors function together. So we will start with the perception layer. So perception layer is basically a physical sensing and actuation interact here directly with this in this layer in the real world. For example, temperature sensor in a hospital room reading patient's environment data every second, or maybe in your room reading the environment and then turning on and off of the air conditioner accordingly. Then we have network layer, transmitting data between devices and internet using Wi-Fi, Bluetooth, etc. For example, a mesh network in a smart factory connecting thousands of sensors wirelessly. Then we have processing layer. It processes the data. It receives, stores, analyze data, cloud server or edge gateways. For example, AWS IoT core receiving thousands of sensors reading per second and storing them in a time series database, right? Then we have application layer. Uh, Application layer, basically it is the user interaction, user facing application that present data and accept commands. A mobile app that shows your home's energy usage and let you adjust your thermostat remotely, or an application that shows you that the temperature of the room is currently 32 degrees Celsius and the temperature outside your home is 26 degrees Celsius. So you don't need to keep the air conditioner on. You can turn it off to save energy and so on. So now we will see the IoT devices categories. Okay, let me give you an example. Imagine a smart greenhouse system. At the perception layer, you have soil moisture sensor, temperature probes, and humidity detectors. These are reading the physical environment. You also have actuators like water pump, ventilation fans. In network layer, handles getting the data from the greenhouse to the server. Perhaps the sensor communicate locally via Zigbee protocol, a low power wireless protocol, to a central gateway, which then sends the data over Wi-Fi or 4G to the cloud. At the processing layer, a cloud service like um AWS IoT Hub receives the data, runs an analytics, and decide is the soil too dry, is it getting too hot, and at the application layer, the farmer using their phone gets a notification. Greenhouse 3 moisture level is critically low and they can tap one button to activate the irrigation system remotely, all four layers working together. You can also take an example from your daily life irrespective of this greenhouse, and you have to explain that in your assignment as well. From your daily life, just look around and see, is there any IoT device working? Or maybe you're standing in a mall and you can see, is there any IoT device here? And you have to explain about that device in your assignment. So now you have two questions of assignment, one for AIoT devices and one for working of all these four layers together from your daily life. Okay, so let's move to the slide number 5, sensors reading from devices. Now we get to one of the two most practical topics in this lecture, sensors. A sensor is any device that converts a physical quantity. For example, it could be temperature, it could be light, motion, pressure, humidity, into an electrical signal that a microcontroller can read and process. Without sensors, an IoT device is blind. It has no knowledge of the world around it. So sensor will provide information to the microcontroller, and I hope you studied the course of embedded system. You know everything about these basic concepts. So the types of sensors we have, digital and analog. Digital signals are the one which produce binary values, 1 or 0 is something happened or nothing happened. And the analog sensors are continuous range of values. How much of something is there, the exact value. Example of digital sensors are PIR motion sensor. It output high when motion is detected and low when there is no motion detected. Similarly, example of analog sensor could be LDR light sensor. Outputs a voltage that vary with light intensity. So let me give you an example. A digital sensor is like a light switch. It is either on or off. An analog sensor is like a dimmer switch. It can be at any point analog or continuous stage. Your microcontroller read analog value through its ADC, analog to digital converter, which turns a voltage say 0 to 3.3 0 volt to 3.3 volt into a number 0 to 4095. It's a 12-bit ADC. So we will go till 4095. I hope you know these concepts from computer architecture and logic design course. So now we will start with the communication protocols. Okay. Once a sensor has a reading, it needs to send that data to the microcontroller. It uses one of the several communication protocols. So what are the communication protocols? GPIO pins, GPIO digital, one signal wire plus ground, single high low pin read, PIR motion sensor button, analog may you have one signal wire plus ground, I2C may you have SDA plus SCL plus power. So I will explain these communication protocols to you in your physical classes because this concept is a bit tough to understand here. So I will skip the communication protocol slides for the time being and we will move to uh, actuators directly. Also these uh, codes. So let's move to actuators, writing to devices. Actuators control method. There are two primary ways a microcontroller send command to an actuator. And what are those ways? Digital write, pin set high, full voltage or low zero voltage. High, you have full voltage and low, you have zero voltage. By fully or on, fully off. Turning a relay on a switch at 240 volt like circuit on. This is an example. Pulse width modulation, analog write, pin rapidly switch on and off many times per second. The ratio of on versus on time duty cycle determines effective power. Setting a DC fan motor to 60% speed, the pin is high 60% of each cycle and low 40%. Okay, let's understand about pulse width modulation. Imagine a light controlled by a very fast switch that flicks on and off 1,000 times per second. If the switch is on for half the time, the light appears at half brightness, or if it is on for 80% of the time, it appears brighter. Your eye cannot detect the flickering. Obviously, 1,000 times per second, your eye cannot detect it. It just sees a dimmer or brighter light. Pulse width modulation uses the principle to simulate different power levels on a digital pin. So let us start from the um, detail of LED light, digital on off. The simplest actuator, a digital write high, turn it on, low, turn it off using PWM, pulse width modulation, with analog write pin 0 to 255 control brightness. The value 0 is completely off, 255 is full brightness. 128 is approximately half in a real smart system. Smart LED stripes like those used in the Philips Hue ecosystem use pulse width modulation to create million of colors combination by independently controlling red, green, and blue channels. So, moral of the story is you how you can turn anything on or off by using this code digital write. Pin is the pin number and high means the value you will set. Then we have this DC motor. DC motor rotates when power is applied. Speed is controlled via pulse width modulation. Higher duty cycle means faster rotation. Direction requires at hybrid driver chip like the L298N, which can reverse the polarity of motor control connection under software control. In robotics, two DC motors with independent speed control allow the robot to turn. If the left motor uses faster than the right, the robot turns right. So how can you use this as in a code? Analog write, pin number and speed. Simple one line statement and you can make the things work. For example, in robotics, you can write the speed of the robot, the pin number at which it is connected, IoT pin number, and analog write is the command. Then we have servo motor. A servo motor rotates at to a precise angle. You cannot you command it with a servo motor, right 90 or 90 degrees, servo right 0 for full left, servo right 180 for full right. Internally, the servo uses its own pearl with modulation decoder to position that shaft. Servos are everywhere in robotics. The Boston Dynamics robot dog Spot uses servo actuator in every joint to achieve precise coordinated movement. So for precise movement, you will use servo dot right and then exact angle at which you want it to move, and it will do between 0 to 180. Then we have relay modules. A relay is an electrically controlled mechanical switch. Your 3.3 volt or 5 volt microcontroller pin controls an electromagnet which physically moves a metal contact that switches a separate, much higher voltage circuit like a 240-volt home appliance. This is how a smart plug works. The ESP32 inside the smart plug cannot handle 240 volt directly, so it controls a relay. You send digital write, relay pin and low command, which is the active state for the most relay modules, and the mechanical contact closes, completing the 240 volt circuit and turning on your kettle. So switches AC DC loads, digital write, pin number low or high, whatever you want to give as a command to the relay. Okay, the concept is the concept like linking all actuators is the control flow diagram on this slide at this site. At the top, the software command, a line of code triggers a GPIO or pulse width modulation pin. That pin signal goes to a driver circuit here, which amplifies it to the voltage and current the actuator needed. The driver the controls the actuator, which produces a physical action in the real world. Every time you write one line of code, you can move something in the physical world. That is the power of IoT. So we are already at 12 seconds. I will start the next IoT as a HTTP client in the next part of the video.